Hello everyone, I am Dr. Saurabh Srivastava, Leader in the Department of Oral Medicine and Radiology, BD College of Dental Sciences, BD University, Lucknow. The topic of today's discussion is radiation physics, in which the first part will be taken up in this lecture. Starting with this radiation, we should know about some history of dental radiology specifically, where the X-rays we can say were discovered accidentally by W.C. Roentgen in the year 1895, and the first radiograph was made by Otto Volkov in 96. Then radiations had their own dangers, and the first paper on this was presented by W.H. Rollins in 1901. There are various techniques of taking a radiograph in the oral cavity. So, bisecting angle technique was given by W. A. Bryce in the year 1904. In the year 1913, the first X-ray tube, which is being used up nowadays also, known as the Coolidge tube, was given by W. D. Coolidge. The paralleling technique of intraoral radiographs was given by F. McCormack in the year 1920. The bite-wing technique was given by H. R. Raper in the year 1925. And then going to extraoral radiography, the principle of OPG was given by Dr. Numata in 1933, and the OPG was jointly given by Patero along with Numata and its principles also in 1948. The myopia technique with the long cone was given by Fitzgerald in 1947, and the prototype scanner of computed tomography was developed by Godfrey Hounsfield in the year 1969. So to introduce the X-rays, these are described as wave packets of energy, and each packet is called a photon, which is equivalent to one quantum of energy. X-rays also, like other waves, are amongst the electromagnetic spectrum, which have other waves like radio waves, microwaves, infrared waves, the visible light waves, ultraviolet rays, X-rays, and the gamma rays. Subsequently, we can see that the radio waves have the longest wavelength and the gamma rays have the shortest wavelength. Now, the wavelength is inversely proportional to the frequency of the waves. And if we see the size of these approximate size, then the radio waves will be approximately to the size of most of the skyscrapers, and the atomic nuclei will be equivalent to the gamma rays. Now, coming to the production of X-rays, where are these X-rays produced? Usually, the production of X-rays is made by an artificial source, which is called the X-ray tube. Now, X-ray tube is placed in a tube head, which is made up of lead, and that inside that lead casing there are some step-up transformers, auto transformers. Oil is there, which immerses the X-ray tube. Now, this is the diagram of an X-ray tube, which has been taken out from an X-ray machine, and the diagrammatic represent the photo and the diagram both are given on this slide. And in the diagram we can see that the X-ray tube, it comprises of a glass tube which is having a vacuumed inside, and it has a cathode and an anode, and the cathode is made up of a tungsten filament, anode is made up of a tungsten target metal which is embedded in a copper block. And this tungsten filament of the cathode is itself placed in a concave shaped cup of molybdenum, which is called as the focusing device or the focusing cup. Now, how these X-rays are produced? We see that this filament which is present on the cathode, it is heated electrically, and a cloud of electrons is produced around this filament. The high voltage or the potential difference which is there between the cathode and the anode, it will accelerate the electrons at very high speed towards the anode. So what is seen is the electrons, they accumulate near the cathode, but with the advent of the potential difference, increase in the potential difference between cathode and the anode, it is being bombarded onto the anode at a very high speed. So this is the diagrammatic representation of the bombardment of the electrons from the cathode to the target metal, which is placed on the copper stem at an angulation. So this bombardment will release X-rays as well as heat. Heat will be produced to about 99% and X-rays will be about 1% or less. This focusing device aims the electron stream at the focal spot on the target, and the electrons bombard the target and are brought to sudden rest. Now the sudden rest is responsible for the transfer of energy. The energy which is lost by the electrons is transferred into either heat, which is about 99%, or X-rays, which is about 1%, as we discussed previously. Now, these tungsten atoms which are present in the target metal, this is the diagrammatic representation of the production of heat, how it is produced. Either it is produced by the deflection of the electron, when the electron which is incoming onto the tungsten atom at the outer shell, it gets deflected from the outer shell electron, producing heat by losing some of its energy, and it is deflected. The other part is where the incoming electron, it deflects along with moving or causing the outer shell electron to move out of its shell, means it transfers more of energy to the tungsten atom and heat is produced. This heat produced is dissipated by the copper block and the surrounding oil, and these X-rays are emitted in all directions from the target. And the X-rays which are emitted, they are emitted by a small window in the lead casing which is outside the tube. So this constitutes the beam which is used for the diagnostic purposes. So here we can see that the representation of the X-ray tube. What happens in the X-ray tube? It is comprising of the cathode with a filament. This cathode is having a molybdenum cup, focusing cup. The anode is made up of copper and it is having a target metal which is having a focal spot. There is a step down transformer which will give up the voltage to the cathode. The electron cloud will form as a result of heating of this filament. Then a step up transformer is placed between the cathode and the anode, and when this creates a potential difference which is of approximately 65,000 volts, it will bombard the electrons onto the target metal and the focal spot, producing the heat and X-rays. So the X-rays will be released through a window which is placed on the casing of the lead which is surrounding the tube. As we have discussed, the tungsten filament is present and the focusing cup is there on the cathode side, and the dimensions of the tungsten filament will be 1 millimeter diameter of the wire which is 10 millimeter in length of the coil, which is connected to step down transformer, and there is thermionic emission of electrons, means on heating electrons are emitted. The focusing cup is either made of molybdenum or stainless steel, and it gathers the emitted electrons in the form of a cloud. The anode is comprising of a copper stem and a tungsten focal spot. The tungsten is taken up as the metal of choice because it has a high atomic number, 94, high melting point of 3374 degrees centigrade, and it has a low vapor pressure, means it does not vaporize very easily, and if whatever vapors are formed, they do not form a pressure. Then the dimensions of this are 1 by 3 millimeters or 1 by 0.8 millimeters, and it follows the principle of line focus, we'll see in the later slides, and it's also called as the target or button. The copper stem, it is made of a copper rod with fins to conduct the heat to the surrounding oil, and the end facing of the cathode has the focal spot embedded at the center. There is a provision of rotating anode also in the full body machines, not in the dental ones. So what is the line focus principle as we have talked just now? We know that the anode, it has an angulation towards the cathode. This angulation is about 17 to 20 degrees over which the target metal is placed. On this target metal, placed at an angulation of 17 to 20 degrees, the X-ray or the electrons, they are being bombarded. And we know the dimensions of this target metal is 1 by 3 millimeters or 1 by 0.8 millimeters. Whenever this is angulated at this 70 to 20 degrees, we can see that this 1 by 3 millimeters, it converts to 1 by 1 millimeter. Suppose we are placing a rectangular object in our hand at the eye level and we angulate it towards ourselves, then we can see that the length of that object is reduced when it gets angulated. So it becomes 1 by 1 millimeter effectively. And this reduction in the focal spot will cause the sharpness of the image. So this angulation will give better heat dissipation, and this emergent beam which is produced with this angulated focal spot will be narrow and it contributes to the sharpness of the image. So we have discussed that there is an auto transformer which will be supplying a voltage of 220 to the tube circuit. The step down transformer will reduce it to 7 volts. We will give it to the filament to produce the electrons, and the filament will get heated up, thermionic emission of electrons will occur. Then a step up transformer will create a potential difference of about 65,000 volts, and then negatively charged electrons will get attracted to positively charged anode, and at a great speed they will be gaining high kinetic energy. So at this kinetic energy, these electrons which are reaching the anode, they are brought to a sudden halt at the high atomic number, the tungsten focal spot, or to a direct hit or a near miss interaction. When brought to a halt, they give up their energy in the form of heat and X radiation, as we have discussed previously. So summarizing this, we can say that from the target metal about 99% heat and 1% of X-rays are produced, and these X-rays can be either due to a continuous spectrum or the Bremsstrahlung radiation or the braking radiations, or they can be the characteristic type of radiations or in the line spectrum. Now these two types of radiations which are produced from the target metal, they are Bremsstrahlung radiation and the characteristic radiation. In the Bremsstrahlung radiation, there is a sudden halt or the braking radiation, it is called. Yeah, there is a direct hit interaction. In the characteristic radiation, it is a near miss interaction. So there is a production of heterochromatic radiations, means the radiations which are produced, they will be having different energy levels and different wavelengths, and the beam which is produced is divergent in all the directions from the X-ray source or the target metal. Now to the production of X-rays, we are coming to the properties of X-rays. What all properties of X-rays can be seen? They can be physical properties, they can be chemical properties, they can be biological properties of X-rays, they can be physical, chemical or physicochemical properties of X-rays. Now the physical properties of X-rays, we have seen that in free space, X-rays will travel in straight lines, and the velocity in free space will be that of light, that is 3 into 10 power of 8 meter per second. The X-rays will obey the inverse square law. That means the intensity of the rays will be inversely proportional to the square of the distance. Means greater the distance, lesser will be the intensity, broadly speaking. So doubling the distance from an X-ray source will reduce the intensity to 1/4. So this will be important principle in radiation protection. No medium will be required for propagation of the X-rays, because as we have seen, the X-rays are produced in an evacuated glass tube. So these X-rays will show the properties of interference, diffraction, and polarization, which is similar to the visible light. They have shorter wavelength and a longer wavelength. Shorter wavelength X-rays will have more energy, so they can penetrate a greater distance of any object. The longer wavelength X-rays are also called as the soft X-rays. They will possess less energy and have little penetrating power. So the energy which is carried by the X-rays, it can be attenuated by matter. Attenuation means either it can be absorbed or scattered or both. The X-rays cannot be reflected, refracted or deflected by a magnet or electrical field, as they do not possess any charge. These X-rays are capable of producing ionization, which is again very important in the field of dentistry or medicine. This ionizing radiation, thus they are called as the ionizing radiations. These are undetectable by human senses because if we are exposed to X-rays, we do not know that we are being exposed. They can affect a film emulsion to produce a visual image, which is produced on the radiograph upon processing. And they may also cause certain salts to fluoresce and to emit light. And the principle behind the use of intensifying screens is this only, because in extraoral cassettes of radiography, where the films are being placed in between the intensifying screens, light is emitted to cause the exposure of the X-ray emulsion. The X-ray beam is made up of photons which are having different energies. The diagnostic X-ray beam can vary in intensity and quality. The intensity is the number or quantity of the X-ray photons the beam has, and the quality is the energy which is carried by the X-ray beam photons. So it is a measure of their penetrating power. So the factors which are affecting the intensity or the quality of the beam, they are the size of the tube, voltage at the kilovolt, peak, the size of the tube current, which is the milliamperes, distance from the target, time is the length of exposure, filtration of the rays, then the target material which is used, means through which the X-rays have to pass. Then the tube voltage waveform, whether it is half wave or a full wave, means rectified or non-rectified. And as we say that the heterochromatic X-ray beam is being produced, all the rays are not useful for diagnostic purpose. The soft X-rays or the rays which are having longer wavelength and lesser frequency, they are harmful to the tissues. So they have to be reduced or filtered. How to filter them? Because these waves, the longer wavelength or the reduced frequency waves will be absorbed by the tissues and will cause changes in the tissues which are harmful. Now, to filter the low energy photons from the X-ray beam to reduce the dosage of the skin, we have to place a filter which is usually placed at the exit portal of the X-ray tube head. So this filter is usually made up of aluminium and it will absorb the long wavelength rays and only allow the short wavelength high frequency rays to pass through it. So the total filtration is said to be inherent filtration by glass envelope and oil, which is about 0.2 millimeters of aluminium equivalent, and the added filtration of the disc of aluminium, which is about 1.5 millimeters up to 70 kVp machines, and 2.5 millimeters of aluminium above 70 kVp machines is there. So collimation is another factor which is taken into account when we are exposing the human tissues. Collimation is controlling the size and shape of the X-ray beam to reduce the tissue exposure and the secondary radiations to give better patient protection and the image quality respectively. So we have to reduce the exposure of the tissues and prevent the secondary radiations from exposing the patient or the film. What is collimation? When we have to shape and size the beam or the X-ray beam, which is usually divergent in nature, what we can do is place a collimator in between the area where we have to take the radiograph. So the area of interest. The various types of collimators can be diaphragm type, rectangular, or cylindrical. These collimators are usually put at the exit portal of the X-ray beam on the X-ray tube head only. So, to summarize this part of the lecture, we can say that we know the X-rays are having the properties of visible light as well as some properties which are of the electromagnetic spectrum, which are having the waveform type of X-rays, and these are high energy rays as well as low energy rays. Some rays are harmful, some rays are of diagnostic quality. Now we know that how the X-rays are produced from the X-ray tube, from the cathode to the anode, the movement of electrons, the sudden halt or cessation of the gained the electrons which have gained high kinetic energy when they are suddenly halted at the target metal, they will be producing heat about 99% and X-rays to about 1% only. And these X-rays will be targeted onto the tissues, onto the area which is of interest through the filtration as well as the pollination to prevent the tissues and give good quality picture. The line focus principle also should be taken into account when we are considering the angulation of the anode. And this angulation of the anode is on the surface of the anode which is facing the cathode. So, to summarize all this, any queries can be put on my email ID. So, thank you. We'll meet up in the next lecture.